Have you ever wondered how the Internet Protocol is able to so successfully connect billions of computers around the Internet in such a way that everyone can send packets to everyone else? Today, I am diving into how the Internet Protocol works, how IP version 4 and version 6 shape the modern world, how a 50-year-old experiment in end-to-end communication drove the development of IP, and more. Come along on this adventure. So today, absolutely by far, the dominant layer 3 protocol is the Internet Protocol. Now, the Internet Protocol originally stood for the Internetworking Protocol, and by the name, it was a way to connect across networks. So let's take a bit of a history lesson on how we got there. So some of you may have heard of the history of the ARPANET. Essentially, in the late 1960s, the US government Advanced Research Projects Agency, or ARPA, which would later become the Defense Advanced Research Projects Agency, or DARPA, formed a committee and started to build out a network of computers across some facilities. Now, these were mainly facilities that did work for ARPA. So these were research organizations, Department of Defense facilities, and major universities. Now, across the original ARPANET, they had a series of routers. They were called the IMPs, the Interface Message Processors. And a host computer would pass a message to the IMP, and the IMP's job was to find the destination of that packet and get it there. And the IMPs were quite complicated packet switches. So once a host computer passed a packet up to the IMP would have to find a route through the network on how to get to the correct destination. And the destination was an address that was made up of an IMP, so 6 bits identifying which IMP it was, and 2 bits identifying what port on the IMP. So we could have up to 64 IMPs on the network, and each of them could have up to 4 computers. So when I addressed the destination, IMP, my IMP would have to find all the IMPs in the hop, forward my packet to them. This was a reliable service, so the IMP would also have to store my packet until it was sure it made it to the next hop, and then the next hop could take it from there. When it got to the destination IMP, it would spit it out to that computer. And that computer could make a new packet, send it back to me. Now, this had some scalability problems. One of the problems was they only used 8-bit addresses. So that's fine if you have only 64 organizations and they each have only 4 computers. But what happens when MIT has more than 4 computers? Well, then they had to buy a second IMP and connect the 2 IMPs together. And then what happens when MIT has more than 8 computers? Well, they have to buy a third IMP. Now, another problem was that just a couple of years after ARPANET, there were some other networks that were starting to come out. So in particular, the one network I want to mention is the French Cyclade. So similar to ARPANET, this was a research project built out of a number of research organizations in France and connected by leased lines from the telephone network. But unlike the ARPANET, they pioneered a technology of unreliable data at the packet layer. So in ARPANET, each IMP was responsible for guaranteeing that the message made it to the next IMP, and then so on and so forth until the message made it all the way to the end. So IMPs had to store a copy of the messages they just sent, so that if they didn't make it, they could resend them again at each hop along the path. This meant, of course, that each router in the network needed to have enough memory to store all of the messages in transit. Of course, at 56 kilobits per second, not a whole lot of messages were probably in transit, but this doesn't really scale well into the modern era. So the French realized is the end host can just keep a copy of the message that it sent once, and if it doesn't make it all the way to the end, it can send it again. And the individual routers in the network don't have to be that smart. So the routers just have to be responsible for forwarding their packet to the next hop, and the hosts at the end of the network are responsible for maintaining the end-to-end connectivity. So the French called this the end-to-end principle. Essentially, a session is between 2 hosts, and the individual routers are only relaying individual packets. They're not maintaining any session state. And this end-to-end principle later became very important when a number of organizations wanted to merge their networks. So as a way of merging networks, they developed the Internetworking Protocol. So with more than one network operating around the world, the ARPANET was primarily in the US, but also extended to the UK and some others. There were a number of networks in Europe and even more networks in the US. So the idea was, with multiple networks, why can't we have a single set of addresses that can uniquely tell us where a host is in the entire world? And then, if I have a network in the US and a network in the UK, even if they're separate networks, like the ARPANET and whatever the British had, they can have some gateways that can exchange these packets across the internetwork boundary. So one of the biggest stumbling blocks in developing the Internet Working Protocol was figuring out how big the addresses should be. The ARPANET had grown at this point to use 24-bit addresses. Some other protocols used different sized addresses. We weren't really sure what would be a good size for how many addresses we'd need. So early versions of the Internet Protocol actually had variable length addressing. So as part of the header, it would include how many bytes the address was, and the routers would look into those number of bytes and find a route. And this seems like a really good idea, but the problem is these routers were forced to handle packets at quite a high speed. And trying to get these packet routers to deal with variable length headers reliably makes them very hard to implement, especially in like a memory safe way. So the Internet Protocol version 4 was originally designed to have a variable length addresses between 32 bits and 128 bits, but they later settled on implementing just 32-bit or 4-byte addresses. And instead of having a variable length to the address, they decided to split up where they define the boundary between the network and the internetwork. So they called this the network class A, B, C, D, and E. So a class A network would have 3 bytes dedicated to the address within the network, and 1 byte to identify which network it was. So the ARPANET, for example, already had 24-bit addresses or 3-byte addresses. So to identify a host on the ARPANET, we put a 10 in front of it. That makes it a full 32-bit Internet Protocol address. We can route it around the world on all the other networks. And we know we have to first find a route to the ARPANET, which is the 10. And once we find a route to the ARPANET's own routing protocol can figure out the other 24 bits. Now, of course, some networks weren't quite so big as the ARPANET, so maybe they didn't need 24 bits. They could be a Class B network, which Class B networks were smaller. They were only 16 bits. So the first 16 bits identified the network, the last 16 identified the host within the network. We also had Class C networks, which were 8 bits. Those were also a thing. Now, of course, by saying a Class A address, what we didn't mean was that the entire subnet mask is a /8. What we meant is that at the internetworking level, the broad overview between all the networks in the world, this specific network of computers fits into a 24-bit space or a /8. It does not mean it's one giant broadcast domain on the wire or any of that stuff. There's still going to be routing protocols within that network. We just didn't want to deal with them at the IP layer. So you may have heard before of the OSI model, the 7-layer model over here that describes the 7 layers of protocols. So the lowest 3 layers are handled by the network, and the upper 4 layers are handled by the individual host. So the lowest layer, we have the physical layer. These are the individual voltages on the wire. Up from that, we have the link layer, which is the actual communication of frames across the link, the data link. And then at layer 3, we have the network layer, which is short for the internetworking layer. It's a term I'll come back to in this video. And the network layer provides a packet service across end-to-end from host to host. And with that packet service, we can build out protocols at layer 4 and higher. Now, in general, most network engineers don't really talk about layers 5 and 6. So we'll talk about layer 4, TCP and UDP, and then we'll skip straight to 7, whatever the application is. So in this video, at the internetworking layer, layer 3, our primary means of data is a packet. So a packet contains a source and a destination, internetworking address. It contains data for the higher level protocol, layer 4, and it's transmitted usually by a link layer protocol, such as Ethernet, but there's other options there too. Another thing that's important to mention early on in the video is the notation we use, because you're probably going to see quite a lot in this video. So in general, at the internetworking layer, layer 3, we deal with IP addresses for the Internet Protocol. And there's 2 forms of these. So the current version of the Internet Protocol, which has been around for 26 years, is version 6. So in version 6, we have 128-bit addresses, that is long, and we break it down into 8, they're called hextets. So each hextet is 4 hexadecimal digits, so those are 0 through F, 16 possible choices there, and each one represents 4 bits. It's also possible to cut off leading zeros within a given hextet if you'd like, and it's also possible to take the longest range of all zeros and compress it with a colon. So that is an example of what a valid shortened IP version 6 address would be. The other version of the Internet Protocol, version 4, legacy IP, uses 32-bit addresses, so that's what it would be like written in hex. We don't write those in hex though, we usually write them in what's called dot decimal notation. So we break up the 32 bits into 4 bytes and then write out each of those 4 bytes in decimal using 1, 2, or 3 digits depending on how many you need for that number. So that would look kind of like this. There's also some weird applications that merge both of those. So in general, it's much easier to carry IP version 4 within the IP version 6 address space and the inverse. So sometimes you'll see a IP version 6 prefix with some dot decimal at the end, and that is usually representing an IP version 4 address encoded as a version 6 address. Not always, but usually that's when you see dot decimal. Another really important concept in routing is the concept of a prefix or prefix length. So you might have heard of what's called CIDR notation or classless interdomain routing. And with this notation, we add a slash and then a number of bits on the end. So you might have an IP version 4 with like a /24, or an IP version 6 with like a /64. This can mean the subnet mask, and if you've seen a subnet mask before, you're probably pretty familiar with that. But it doesn't have to. It can also mean a routing prefix, which is an aggregate of multiple subnets, or even a single address, like a /32 or a /128. So at this point, I want to make you guys all very familiar with all of the fields in an Internet Protocol header. Of course, I'm going to go into them in more depth throughout the video, but just kind of want to lay it all out there so you have a baseline getting started. So this is Wireshark. So in Wireshark, I've done some captures of DNS. It's a nice, simple protocol. And so essentially in Wireshark, these are all packets that have flown over the wire. And this is a specific packet that I want to look at. So Wireshark has captured it. This particular information here just shows me the capture information from Wireshark. And then everything below that is the actual bits and bytes on the wire. So you can see here on the wire on layer 2, we're using an Ethernet 2 frame. And I'm sending it from my computer, which is MicroStar, it's MSI, to EAC Automation, that's my router. So this is the MAC address of my local computer, and that's the MAC address of my router. Now in this case, that router is my default gateway, so that makes sense. I'll get into what the default gateway is a bit later in the video. But for now, just know that we know the MAC address due to layer 2 discovery. My past video on layer 2 goes a little bit into what neighbor discovery is in layer 2. But that comes back for us here in layer 3. And last thing we have is the ether type, which in this case is Internet Protocol version 6, 86DD. So then we just keep nesting our headers. So this is our layer 2 header. We have a layer 3 header, layer 4 header, and layer 7 header. Remember we kind of forget about layer 5 and 6? Yeah, so here's our IP. And so in this case, the first 4 bits are the version number, which in this case is 6. We then have a number of other fields such as traffic class and flow label. And I'll explain these later, but they're in there. Next we have the length of the payload. So this is 90 bytes on the wire. That's what we figured out from Ethernet. We subtract our layer 2 and layer 3 header, and it says there's 36 bytes remaining. So that includes everything after the Internet Protocol. It says our next header is UDP. A hop limit is 64, and we have a source and destination Internet address. Now remember, the goal of the Internet Protocol is to be able to uniquely identify every host on the Internet by its address. So in the IP header, we have our source and destination IP address. And as our packet traverses the Internet, we never change these. So back in layer 2, our MAC addresses were only valid on the same broadcast domain. So we could have duplicate MAC addresses in different VLANs, duplicate MAC addresses around the world. And that wouldn't matter, because as soon as we start transitioning between networks and routing packets, we're up at layer 3. We don't care about the layer 2 addresses anymore. But in layer 3, we do care about these unique addresses, and we do hope that they're unique around the world. And of course, in IP version 6, we have so much address space that everyone can have their own address space. All addresses can be unique. But in IP version 4, we had some challenges maintaining this uniqueness. And I have a whole chapter, I don't know, somewhere around here that describes that. So fundamentally, routing decisions are based on the destination address. The routers are trying to get our packet to its destination. Now the server we're talking to is going to need our source address so it can send packets back to us. And the software is also going to need to know this next header so that it can decide how to decode the packet. In this case, it's a UDP packet. So we jump into UDP. So in UDP, we, instead of having addresses, we have port numbers. So at layer 4, we're identifying services within a host. So we use port numbers to identify those. So for example, if I have both SSH and HTTP, those use different port numbers. So they're the same host, the same IP address, but different port numbers for different services. We again have a length. This is 36 because it includes our own header this time, and some other checksums and stuff. So the 4 fields we're most concerned with in the IP packet are the destination IP address, the source IP address, the next header, which tells us what protocol is encapsulated in this IP packet, and the hop limit. And in case you're doing any legacy stuff, we have a slightly different ether type here, so 0800 for IPv4. Our header is not all that much different. So we have a different version number, version 4. We have a slightly shorter header in this case. We have some additional flag bits here in IPv4 we didn't have in v6. So that includes the don't fragment bit. And we similarly have a protocol, we similarly have a time to live, and we have source and destination addresses. So some of the fields just changed name a little bit for clarity. The hop limit is the same as the time to live. They serve the exact same purpose and they're treated the exact same way. In IP version 6, the next header is used to define the protocol. And that's because there are some protocols that kind of make a shim header. They sit in between. So it's not necessarily a protocol header. It might be another IP layer header, for example, for IPsec. And fragmentation is just not allowed in IPv6. It causes too many problems. But in IPv4, it was a thing, so we have some additional fragment bits here, which cause some disasters. Beyond the IPv4 header, though, the UDP header is exactly the same. We still have our source port and our destination port, our payload, our checksum. So while we're talking about IP addresses, some IP addresses are special. So in IP version 6, all IP addresses are considered globally scoped unless otherwise noted. So this means that you technically could use any address you want in the entire IPv6 address space, except for the ones that are special, to communicate, and it should work just fine. Now for special addresses, anything that starts with FF is multicast. So this has its own set of rules. Later on in the video we talk about that. Next up for special things, we have FE80. So if the address starts with FE80, it's a link local address. This means the address is valid on the layer 2 domain, but not farther than that. So FE80 addresses cannot be routed. They can only be valid on the local link. And also, we always have an FE80 link local address for every host on the local link. And that's how we do things like neighbor discovery and router advertisements. It's also possible in IPv6 that you don't need anything but the FE80. So since they're there automatically, protocols that just need to talk to each other, like OSPF or Multicast, if you're using MDNS, some private backend networks, you don't even need to assign addresses. You can just use the FE80s. Now everything else is a routable scope, but that doesn't mean it's valid all the way to the internet. So there's a deprecated range you might still see occasionally, that's FEC0. So if you see that, that used to be called the site local range. We got rid of that one though, so it's not around anymore. Its replacement is FC00/7, which is realistically FD00/8. That is the unique local address space. So to properly use the ULA space, you have to randomly generate a 48-bit prefix that starts with FD. And then within this 48-bit prefix, you can do whatever you want. So you can make /64 subnets, you can use it across multiple sites, you can use it on just one site and make new ones each time. You're not supposed to assign them sequentially, you're supposed to generate a new random one each time. So these are really commonly used in routed setups where you're not accessing the global internet. So there are some overlay networks, for example, that use ULA addresses. It's also relatively commonly used on networks which are isolated from the internet. So for example, like a management network or a backend storage network where you have routing, but you don't have internet access. Those are basically the intended use cases for ULAs. So the only addresses we allow on the internet, mostly by convention, are 2000/3. So that's any address that starts with a 2 or a 3 in the first digit. So these are the ranges that are officially assigned by IANA for the internet use. So they've gone a step further and they've assigned the second digit to indicate which regional internet registry they've assigned it to. So for example, 26 and 27 both went to Aaron, who is in North America. 2A went to RIPE, NCC, in the EU. So you can kind of tell from an address if it's like a 26 or 2A what country it was assigned from. Now this does not absolutely mean what country the server is in. It's more like what company the headquarters of the company that bought the IP is from. So for example, my website is hosted in Ashburn, Virginia. My address starts with a 2A01 because the hosting company is a German headquartered company, Hetzner, and so they bought a range from RIPE out of RIPE's prefix 2A, and they're using that across all their data centers. There are some other prefixes that are special. So 2001 DB8 is a documentation prefix. 3FFF/20 is a new documentation prefix as well. 3FFE was the test IPv6 network called 6-bone. There's a couple other special spaces like this that have special rules. But generally, the protocol doesn't treat them differently. It's also on the low end of the prefix space, ::1, the first address. That is the loopback address. There's only one loopback address. :FFFF:0:0. So that's a 96-bit prefix. That is used for IPv4 mapped IPv6 addresses. So in software, you can use an IPv6 address where you encode the IPv4 address into the last 32 bits and then stick FFFF in front of them. And that tells the operating system that you actually want to do a v4 call instead of a v6 call. So as software, you can use only IPv6 sockets and IPv6 programming interfaces, but still be compatible with both v4 and v6. On the v4 side, addressing is a bit of a nightmare. So originally, they took their 32-bit space and they split it in half. They said the first half of this is class A. So these are the big networks. Then they took the remaining space and split that in half. That's class B. So now we have a half of a half. Then they took the remaining quarter, split it in half again. That's class C. Then they left the last eighth free for future use. Eventually they came in and split that again in half, and now we have class D, which is multicast, and they again left half of that for future use, which is now called class E and reserved. So again, like IPv6, multicast has special rules associated with it. Further on in the video I talk about those. The class E space, nothing actually prevents you from using the class E space. It's not routable on the internet because it's not a valid address, like not assigned by IANA address. But some cloud providers are starting to use the class E space because they just don't have enough space for their back-end infrastructure in IPv4. There's also 0/8 is reserved in IPv4 where it's not in IPv6. 127/8 is an entire /8 just for loopback, which is kind of an insane amount of loopback, but it's what we had in IPv4. There's also 3 specific regions that are designated as private use. So that's 10/8, which was formerly the ARPANET. So the ARPANET was deprecated. The IETF used its former prefix as a private space. There's also the 172.16/12 space. This is from 172.16 through 172.31, not 32 and 33. Don't be those guys that use it. We also have the very famous 192.168 space /16. So those are also private. Also on the train of private networks, 100.64 is reserved for carrier grade NAT. So for ISPs that do NAT, 100.64 is where they should be going. Plenty of them still use 10 also though, which is not great. And there's also plenty of network operators that use like 6, which is the DoD prefix. Well, the DoD owns 6, 7, 11, they have a bunch of them. And they don't route them on the internet because they're private for the DoD. But some ISPs, cellular ISPs, use 6 as their CGNAT prefix. Some companies spill in from 10 into 11, which is also the DoD space, so I guess I got lucky there. Some of them claim to have spilled into 12, which is owned by Bell Labs. The big problem that comes up in v4 a lot is that we don't have enough address space, so we steal other people's, or we reuse it, or we NAT our way through it, and we just don't have that problem in IPv6. So anyway, watch your address scopes, especially your FE80s, they are special. So now we've constructed a packet. It's got an IP header, it's got some data, and we want to forward it through the network to its destination. So over here I have I guess you might call it a map of the US with some major cities. Yes, I know Toronto is not in the US. So let's say, for example, I am up here, and I have a link to the router in Chicago. And I want to connect to a server down here. So my server down here, he is connected to a router in Phoenix. So now I have constructed my packet, I send it off to the router. How does the router know where to send it to? So in this case, the router, I guess, has 4 choices. So it can send it to Seattle, Dallas, Atlanta, or Toronto. So now remember, there's not a whole lot of information in an IP header. So there's only 8 fields. So we have version, traffic class, flow label, size, next header, hop limit, source address, destination address. 8 fields. Of those, some of them are not going to be useful at all to a router. So first off, the version field, that's always going to be 6, at least for IPv6, before for IPv4. So aside from telling us how to decode the packet, which we could have also gotten from the link layer ether type, it's not a particularly meaningful field. Also, the length, size, and the next header both are used by the destination to see what's inside the packet, and a router on the route isn't going to gain any information from that. So that leaves us with traffic class, flow label, hop limit, source and destination address. So of these, the only 2 fields that a router really spends a lot of time looking at are the destination address and the hop limit. So fundamentally, the destination address tells us where our packet needs to go, and our router needs to look at its routing table to figure out how to get there. So conceptually, I could come up, there's 1, 2, 3, 4, 5, 6, 7, 8 nodes in my network. So each of these routers could potentially have a table that lists all 8 nodes and just says what is the optimal path to that node. So for example, for my node here at Chicago, I could say, so I'm RD, so that doesn't help me at all. So if I want to go to YYZ, Toronto, and I probably want to take the route towards YYZ. So when I get to IAD here, I could take 2 paths. I could go YYZ or I could go ATL. And so I guess we'll just say, for simplicity, we'll go via Atlanta. ATL, go to DFW, via DFW. And Phoenix, I could again get there either via DFW or by Seattle. So we'll just say, for this example, we're going to DFW. And LAX is fastest via C. So that's what my routing table looks like right here at ORD. But what about that same table over at LAX? Let's make a copy of that over here. So ORD, my fastest path is via Seattle. YYZ, my fastest path is also via Seattle. So we go Seattle to ORD to YYZ. IAD, so I have 1, 2, 3, 4 hops there. 1, 2, 3, 4 hops there. So I could take either Seattle or Phoenix. Say Phoenix for now. Atlanta, I'm going to go by Phoenix. DFW by Phoenix. Phoenix by Phoenix. Seattle by Seattle. And LAX via me. So each of these 8 nodes has to come up with this table of how to get to every single other router on the network. Now that kind of sounds like a pain in the ass, doesn't it? So even in IP version 4, legacy IP, there are 4 billion valid addresses. Now the Class D and the Class E space aren't included because those are multicast and reserved. But still, that's like a heck of a lot of addresses to have in memory all the time. And that would be kind of impractical. Nevertheless, this is the exact solution that the early ARPANET used. Now they only had 6-bit addresses, so they could only handle up to 64 routers. So for them, 64 lines in a table was not that bad. But for us, we need a better way. So I reworked my drawing a bit to give everybody an address. So each of my routers now have an address. This is just a single address. That's the address of the router itself. And so these routers just need one address because they're just a single router. But then over here, my cable company, they have a really big route. So they have a /32. So they have 2601.420/32. So everything that's within this prefix space is owned by this router at my cable company. And similarly, the server I'm accessing has a really long address. And their hosting provider also has a prefix, in this case, 2A01.69.69. So these prefixes aggregate. So my particular network is maybe a /64. Maybe my cable company gave me a /56 to make subnets out of. And then that aggregates into maybe a /48 or /40 for my neighborhood or the local POP for that ISP. And then ISP aggregates that into a /32 for all their customers in Michigan, for example. And the hosting company probably does the same thing. They gave each server a /64. They aggregate those across their data centers. This /32 might be a single data center, for example. And so they're advertising out on the internet that they have a specific chunk of the IP address space. In this case, they have a /32 of it. So that means that in IP addressing, we chop off everything after the first 32 bits. So in this case, just the first 2 hextets. And that becomes our route. We inject that into the routing table, and every router needs to find a route to this prefix instead of every single address individually. So now in this example, we have 10 routes, because we have the 8 backbone routers, and then we have my cable company and the hosting provider. So the route at ORD will look something like okay, so here is my routing table at the ORD router. So first I have all of the addresses of all of the routers, because those are just individual, and so I'm going via the link to YYZ, going via the link to Atlanta, etc. And then I have these 2 routes that are from my 2 ISPs. So I have the cable company, so I have a dedicated link from here to the cable company, and then the hosting provider here has advertised its 32. That's gotten propagated across the network, and it's made its way to ORD, and we figured out that the best way to get there is via DFW. I send a packet from here to my cable company. My cable company sends it to the router ORD. The router here is going to look and see the destination is within that 2A016969 prefix and say, aha, that matches this line in the table, so I need to go via DFW. Send it down to DFW. Now, what does DFW do? So now I can rewrite this table from DFW's perspective. So now here at Dallas, it has this routing table. So its next hop to get from where it is closer to the hosting provider is to take this link here. So in that case, that's via Phoenix, goes off to Phoenix, etc. We get on the same path. So essentially, a routing table is a couple of things. It's a list of prefixes. So each prefix is an address and a length, and those are the routes. And then it's a next hop of how do we get closer to that prefix. So now every router has its own view of the routing table, and that view of the routing table is where it should send a packet to get closer to its destination from its particular location on the network. So in this case, all of my 8 routers each have a different view of the world, so to speak, because they're each wired differently. They're each wired in different points and connected to other routers differently. So for each of them, they would suggest a different route for a packet. So how those routes get there is a very complicated topic, but for now, let's just assume those routes are there. Now there's one last thing a router has to do before sending its packet out, and that's that it has to decrement the hop limit. So of the 8 fields in the header, version, traffic class, flow label, blah, 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 the hop limit is modified by routers. So this is used to prevent routing loops. So let's see what a routing loop might look like. So imagine I send my packet over to Seattle, and due to a bug, Seattle decides, my next hop should be ORD instead of Phoenix. So it sends it back to ORD. And ORD looks at it and says, my next hop should be Seattle. So it sends it to Seattle. And a single misconfiguration of a single router can cause this packet to just keep bouncing back and forth all the time. And that's kind of a bad thing, right? So if you remember in layer 2 bridging, packets could loop around our network forever. And that was a bad thing there, and it's still a bad thing here. So on layer 2, we would turn off some links to prevent that from happening with spanning tree. But in layer 3, we have a much better solution. We're going to drop the packet if it ends up going through a loop, so it can't cause us any more problems. So that's what the hop limit's for. When a host sends a packet, it initializes the hop limit to some value, probably like 64 or 128 or something like that. And each time it goes through a router at layer 3, it subtracts 1 from the hop limit. Now, as soon as the hop limit reaches 0, it can't get forwarded again, but it can get accepted. So if I send a packet with a hop limit of 0 on the local network, it can get accepted by the destination, but it can't get forwarded by a router. If I send a hop limit of 1, I can go through exactly 1 router and no more. So this will prevent the packet from bouncing back and forth forever, because once the packet's hop limit reaches 0, it just gets dropped, and we, hopefully we fix our routing problem by then, but at least we don't have a flood of packets tying up the whole network. So I'm in a Linux system. If I just look at my routing table, here is what the routing table looks like on this example system. So it says 2A01 DB8 64 via dev Ethernet 0, so that's a specific link. FE80 via dev Ethernet 0. Default via FE80 blah, 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 and a multicast route. So So essentially in Unicast I have 3 routes. So I have this 64, and a default route. Now on virtually all networks you use, you're going to have a default route, and this is essentially a /0. So one thing I didn't mention that is that routes are prioritized based on how long they are. It's called the longest prefix match. So in this example, I have a route called 2A01DB8::/64. And I have another one called default, and default is essentially 0/0. So 0/0 should include every address that's valid, right? But instead, we're going to take the route for 2A01DB8 because it's more specific. So if you have an access of a route to, say, 2A01/16 and also 2A01DB8/32, you'll take the more specific /32 route instead of the less specific /16 route. So now there's 2 different kinds of routes we'll see. Routes which are on link and routes which are via a gateway. So coming over here again, we've got a couple different routes. So this route and this route are both on link, so dev eth0. And this route, default, is via this gateway. So this is the IP address of the gateway. And in this case, there is no gateway, it's just the device, Ethernet 0. So essentially what this means is for our route which is on link, we can directly contact the destination. And we have to figure out via the link layer or the tunnel adapter where the destination is. For routes via a gateway, that means that that gateway is the IP address of a router. And we need to send our packets to that router, and the router will know what to do with them. So the process of finding a host on link is called neighbor discovery. So I went into it a little bit in my layer 2 video in the past, but I'll go into it again here. Future Apple Art and Editing, I actually covered this later on in the video in much better detail, so it'll come. So when asked to route a packet to that destination, this computer chose to find it on link. That's what its routing table told us to do. It found the MAC address, the link layer address, and now it can send an Ethernet 2 frame to the correct MAC address with the correct destination packet. So it also can store that MAC address in its neighbor table for next time. But what about this default route? So this is our gateway, but there's no field in an IP packet for a gateway. So where does this gateway come in? So just to prove that to you, I have a ping here. So it's from my IP address to another IP address. And nowhere in here do we have that FE80 address of the gateway. So where did it go? Because we're sending the packet to a destination. But what do we do with that gateway? So essentially, the only purpose of the gateway address is to find the link layer address where to send the packet. Because ultimately, all of these routing tables need to point us in the direction the packet needs to go. So if we're on an Ethernet link that can take us to the destination, that's great, we go there. But if not, we need to find a computer that can. And the only place we can send those packets is via our Ethernet link layer. So we need to find a link layer address we can send this packet to. And the IP address is kind of a shortcut for that. So we take the gateway IP address in that routing table, and we do neighbor discovery on that IP address. And that gives us the MAC address of the router. Now, our IP packets that have a destination can go to the MAC address of the router, and the router can forward them. So before sending that packet, my node actually did a neighbor solicitation looking for the address of the gateway, FE80, 083, E3, blah, blah, blah. And in this case, it actually already knew what the MAC address was, so it sent it there just kind of asking to confirm because it wasn't sure if it was still valid. It was nearing timeout. But it could have done the same neighbor discovery process with an unknown MAC address and asked the gateway to respond with its link layer address. So a neat quirk of this is the gateway doesn't have to have an IP address, it just has to have a MAC address. So, and it doesn't even have to have an address of the same family. So in some operating systems, it's valid to put in a IPv6 gateway address for an IPv4 route, because all we're doing is looking up the MAC address anyway. That IP address is not involved in sending that packet. So I know this is a layer 3 talk, not a layer 4 talk, but I think the transmission control protocol deserves some attention here. So the transmission control protocol itself actually predates the Internet Protocol, and it was designed as a replacement for the previous protocols that ran over the ARPANET, based on the lessons learned from the French Cyclade project. So in short, the transmission control protocol provides the application layer with the emulation of a stream of bytes, so bytes which are transmitted in order. in both directions. This stream of bytes is then broken down into packets at the IP layer, sent across the network where they may potentially be lost because we're not relying on the routers anymore to do packet replication, and reassembled on the other host to be transferred up to the application. This also provides things like error detection, checksums, and reordering of packets. So if they arrive out of order, they'll get reordered back in order. If any get lost, they'll get retransmitted. So here I have an example of a simple TCP session. This is actually carrying HTTP, so we'll just ignore that for now. So the beginning of our session is setting up the session, so we need to synchronize and establish a handshake. After that we can exchange data, and then we can close the session. So TCP is based on a session, so we're going from a port on an IP address to a port on an IP address. You may have heard the term ephemeral port before, or ephemeral source port. So in this case, I'm going to port 80, which is the well-known port for HTTP. But I also need a port number on my end, my application end. So because I'm not on a web server, I don't have an assigned port. So we just take a random one from the high-up port numbers to use as our source port. And that way the web server can identify us just as a random high-numbered port. This is all dealt with by the application. But at the IP layer, we need to be aware of that these high-numbered ports are essentially randomly assigned. We don't really know what the ports mean. They just come from a pool. So the handshake here to establish the session requires a SYN, a SYN-ACK, and then an ACK. And then we can send our first data. So here in our first packet, so we're going from my IP address to the server, and we're going from port 57032 to port 80. So because this is a layer 3 talk, I'm not going to go into the details of TCP congestion control and window size and things like that. But the MSS field in particular is kind of important to us as network engineers. So when TCP sends data, it never sends a layer 4 packet bigger than the MSS, the maximum segment size. So this is the most data we'll ever put in one packet. And essentially this prevents the IP layer from having to fragment the packet. So ideally, two hosts could establish between them what is the largest packet they can send, then subtract out the layer 3 header and the layer 4 header to get their maximum segment size. That's how we get 1440. We have a 20-byte header for TCP, and we have a 40-byte header for IPv6, and a 1500-byte MTU or packet size at layer 3. So both sides will actually send the MSS to each other, and there's nothing preventing them from having a different MSS on each side. It's perfectly fine. But usually, most links that we run IP over are bidirectional. So we'll want to have the same MSS in both directions, and if we're running network equipment that lowers the MTU on layer 3, it's a good idea to also lower the MSS on layer 4 in TCP. Now, TCP can do a technique called path MTU discovery, where it sends packets that are too big and gets a reply back that's saying they're too big to determine what the MSS should be. But we can also help it along by using MSS clamping if we're doing anything that lowers our MTU, which is basically having the router rewrite the MSS in the TCP packets so that it's smaller. So a couple things I will mention as TCP design that impacts layer 3. The first thing is that TCP treats every error as if it was a bandwidth restriction. So in general, in the early days of networking, if a router became overwhelmed and could not process packets fast enough, it would just drop them. That makes a lot of sense. It's an easy approach. And essentially that means that for TCP to see that packets have been dropped, it assumes that they were dropped because some router somewhere was having a hard time keeping up processing them. It could have been because they were corrupted on the wire, then we just see one single packet dropped. But if we're seeing a continuous stream of drops, we believe it's because we're sending them too fast for the routers to handle. Now, of course, I may be connected at, say, 10 gigabits, so I can send data very fast. But somewhere along that link, it may drop to a gigabit or even 100 meg. And I don't know that. Neither side of the connection knows that. So we basically rely on this fact that routers along the path will drop packets as they can't keep up as a method of signaling to TCP that it should back off in how fast it's sending data. Now also, packets which are out of order are believed to have been caused by a similar problem. So if packets arrive out of order frequently, TCP will start backing off on its windowing algorithm. And this is a case where at the network layer, if we're doing anything with link aggregation across multiple links, it can certainly cause problems for TCP if packets are consistently arriving out of order if we're taking multiple paths. That's why at layer 3 and at layer 2, we go through a lot of effort to make sure that a single TCP session should always take the same path, so it doesn't end up on paths with two different latencies. So before I move on from layer 4 protocols, at this point I've mentioned UDP, which is a very simple method of encapsulating a user space data into a packet with a port number. TCP, which is a much more complicated way of setting up a session between two services and two hosts. There's also a third user space protocol commonly used, that is SCTP, Stream Control Transmission Protocol. And I say that because a lot of network administrators forget that it exists and basically have a rule that says allow TCP, allow UDP, and block everything else. And that causes us to have to develop applications based on UDP that should have been developed based on SCTP. Quick initially was going to use SCTP, and they ended up re-implementing SCTP over UDP. WebRTC had to do the same thing because SCTP kept getting blocked by people's fireballs. So be aware there's more out there than UDP and TCP. But in general, UDP is the simplest end of the spectrum. TCP is on the complicated side, and everything else kind of fits in the middle. So I mentioned the Internet Control Message Protocol, or ICMP. And this is sort of a Swiss Army knife of managing the IP layer. So in most of the layer 4 protocols, we identify a specific service on a host. But in ICMP, we identify the host itself, and we carry kind of extra information that the IP layer couldn't carry in its fixed size packet. You've probably heard of this before as the ping utility, which looks kind of like this on the wire. So I can ping. So we got the name of a host I'm going to ping, and we'll go. And so we sent it 56 data bytes, and it's coming back just fine. So over in Wireshark, I'm just filtering an ICMP, we have a ping. So like everything, we have an Ethernet 2 frame on the wire, we have an IPv6 header, which includes our source and destination address. And our destination in this case is, in fact, 2620 FEFE. And then we have our Internet Control Message Protocol. So in this case, we don't have any sort of port number, we have a type and a code. So the type in this case is a ping request 128, and the code is 0. And in this case, we said we also have 40 data bytes, which includes the header, get us to 56. And they just look kind of random. In fact, 10, 11, 12, 13, 14, 15, 16, yeah, they're sequential. So ping is a pretty simple command that just sends this echo request. And when we send an echo request, we expect the host at the end of this to process ICMP and send back an echo reply. So unlike TCP and UDP, which end up getting processed by the layer 4 transport and the application layer, ICMP is directly processed by the host. And I believe in every operating system it's done in the kernel. So the host, of course, sends back an ICMP message, so it's from 2620 FEFE this time. And it's an echo reply, 129, and it has the same data, 10, 11, 12, 13, 14, 15. So very simple. We just send a bit of data. We expect to get the data back. And this is a really simple way to tell if your network is working. When you ping a host, that proves that the host is able to communicate with you through all of your routers and your whole network. So this is basically a basic diagnostic tool. So what if I try to ping too big? So let's say I want a size of 1800 bytes. What do I get? Well, it seems like it worked, but what actually happened? So here we have an interesting bit. So it says 422 bytes on the wire and Ethernet 2, but then down here it says we have a frame and a reassembled IPv6. So 1808 bytes. So remember how I said in IPv4 we would fragment, unless you had the don't fragment bit, in IPv6 we don't? Well, that's kind of a lie. So in IPv4, if a packet was too big for a router to send on the next link, the link packet size was too small, it would split it up into smaller packets, send those as fragments, and they would get reassembled later. Now, this put a lot of work on IP routers who were on the route to have to deal with fragmenting other people's packets. So in IPv6, we got rid of that entirely. However, an individual host is still allowed to fragment a packet and send it all the way to the destination as fragments, but nothing along the path is going to change that fragmentation. So what happened in this case was I said I want to send 1800 bytes. That's bigger than the size of my link, so split it into two parts. And it added a next header saying it's a fragment. So remember how in IPv6 we call it the next header instead of the protocol? One of the reasons is because these shim headers can get inserted as a next header. So a router on the path only has to look at the original header to do its routing, and any additional information goes in the next header. So in this case, I have a fragment header here. So my next header is a fragment header. And the fragment header contains the information we need to reassemble the fragments. So what if I wanted to stop doing that? What if I say MDO? So that stands for don't fragment. So we're going to try to send 1800 bytes, but we're not allowed to fragment them. Now I get an error, message too long. So message too long comes from Linux itself. Linux itself says I can't send that packet, it's too big. So I'm going to force it to send it on the wire. Let's see what the router does. So I got an ICMP reply that says packet too big, and then the local system says message too long. So over here in Wireshark, here's my ping. So in this case, I'm on 2001 DB81, and I'm going to 2001 DB82. So I'm crossing a router, and I'm sending a ping request, and no response was seen because I sent too much data. But instead of a response, I get back this. So it came from 2001 DB11, which is the router, and it's sent to me, and it says type, packet too big, code 1, and then here we have an IP and an ICMP header, which is actually my original packet. So basically, my MTU locally was big enough that I could send my packet to the router. The router then had a link with a lower MTU, in this case a standard 1500, mine was 2000. So it couldn't forward the packet any further. Instead of fragmenting it, it sends a reply back to me that says, hey yo, message too big, you gotta do something about it. And to help me piece together the pieces, it sends back the headers of my original packet, as much as it can fit. So in this case, I got the IP header of the original packet and the ICMP header of the original packet and some of the data. And so now my operating system can look at that included header and piece up which connection caused the error and preventing it from doing it in the future. That's why in this case, it only happens once, because after that, my local system remembers that that route can't have packets so big, and it won't send them anymore. So protocols like TCP can use this to start with big packets and progressively go down until they find out what MTU actually works on the whole path. So if I have a 2000 byte MTU to my local router, which has 1500 bytes to its next router, which might have, say, 1496 if it's using PBPoE or something dumb like that, then I can keep sending these and finding out what the MTU is on each hop in the path and make sure I'm maximizing the amount of data I can send, even in the presence of funny links like this. Next thing I'm going to try is pinging an address that doesn't exist. So 2001 DB8 is documentation prefix. I don't have anything in my test set up with a :3. So I get destination unreachable, no route. And if I look back in here, Wireshark has so kindly highlighted them, so my ping went out and came back as a destination unreachable. So in this case, it's an ICMP type 1, unreachable, and the code is 0, no route to destination. And again, we include the original header that caused the problem. So for a lot of cases, if there's an error in processing your packet, whatever device or router had the error is going to kick back an ICMP packet, just like this. And by looking at these types and these codes, we can figure out what's causing the problem and diagnose our network better. Now, of course, not all software is going to respond gracefully to these errors, but as a network admin, you can always pop up Wireshark, see what's going on, filter for ICMP or ICMPv6, see if there's any errors flowing. So, of course, a few other errors we can get back. So we can get address unreachable. We can get no route. And one more, the router could say administratively prohibited. It's kind of going over on the next line. So administratively prohibited is a nice way of saying the firewall blocked you. A lot of firewalls don't send this, they just drop the packet. But if you kick back an ICMP administratively prohibited, then it makes debugging your network a lot easier. Another cool protocol we can build out of ICMP is traceroute. So you've probably seen movies where they're like, tracing the hackers through the world. It doesn't work anything near like that. But what really happens is we basically set a really low hop limit. So if you remember, routers will always decrement the hop limit, or the time to live, every time they forward a packet. And that prevents the packet from going in a loop forever. Because once that hop limit reaches 0, then the router has to drop the packet. It's been hopped too many times. So what the router can do is it can kick back an ICMP packet that says hop limit exceeded. And so hopefully the ICMP packet doesn't also end up in a circle, because it could happen too. But if the ICMP hop limit exceeded packet comes all the way back to the host, then we know that we took too many hops. So what traceroute does is it sends a packet, either an ICMP or a UDP packet, with a hop limit of 1. And it gets back an ICMP hop limit exceeded. And then it sends them with a 2 and it gets it back. And it goes all along that path, and it can see all the IP addresses of the routers that it went through at each time it exceeded the hop limit. So I asked it to trace the route to 2001 DB822, and it took 2 hops, so we went through 1-1, and then we hit 2-2. So in this case, it worked over UDP. So send a packet to the final destination, 2001 DB822, and it set the hop limit to just 1. And so a router along the path, 2001 DB811, sent us back a code 3 time exceeded, hop limit exceeded in transit. And so this tells us that, and then of course the rest of the packet. So this tells us that this must be our first router because that's where hop limit of 1 was reached. So in this case, it sent that 3 times to see if there were possibly 3 different routers. So then after that, it ups the hop limit to 2 and tries again. So it's sending a UDP packet to same destination, but 1 more on the hop limit. And this time it got back from 2001 DB822 a ICMP destination unreachable, port unreachable. So our random UDP packet made it to the destination. The destination says, I have no server on that address, and sent us back an ICMP message. Some devices are nice enough to do this to you. A lot of them will just ignore you if you send to a random place. So you might see in traceroute that all of a sudden it starts to go star, 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 star. And that's because whatever the last device in the path was starts dropping your packet. And so traceroute just keeps increasing the hop, hoping that you'll find something and won't. So everything I've just mentioned is exactly the same in IP version 4 and version 6. Some of the numbers are a little bit different for the error codes, but all of those error codes apply equally to v4 and v6. We can do ping, we can do traceroute, address unreachable, administratively prohibited, port unreachable, hop limit exceeded. All of those things are the same in v4. Now in IPv6, ICMP does a whole lot more. So back in IPv4, we had a mismatch of random protocols that would do things. So we had ICMP, which did ping and it did unreachable and things like that. We had a protocol called IGMP that did multicast. We had a protocol called ARP that would do neighbor discovery. That's actually a layer 2.5 or kind of a link layer protocol. We had DHCP to configure single addresses on hosts. And all of those things got wrapped into ICMP v6 and IPv6. So it's a much more cohesive protocol. It's not a bunch of random stuff going on. So first thing I'm going to look at is neighbor discovery. So my IP address is in this same subnet here, 2001 DB81420. And I sent him a ping and I got a response back. So when we take a look at that ping, it's going from my address to his address, but it needed to figure out what the MAC address was for the source and destination. So the source is my address, but what is his address? How do we figure out his MAC address? So I already talked about how this works a little bit in my Bridging the Ether video up here. But basically, if you recall from earlier, if we're on the same subnet as the destination, we go directly on the link layer. And if we're out of that subnet, we go to our router. So we need to find the link layer address of our destination, or neighbor. And in IPv6, we use a process called neighbor solicitation or neighbor discovery. So here's the neighbor solicitation I sent out. So I am 2001 DB810, blah, blah, blah. And I'm sending it to called a node solicited multicast address. So I've coded in some bits of the address I'm looking for into this multicast address. And I say I'm doing a neighbor solicitation and here's my target address. So in IPv4 we would send an ARP request. This is similar. ARP would go to everyone though, so it would flood to the entire broadcast domain. In this case, because we're using a multicast address, a proper multicast system, and a multicast is further in the video, but a multicast router or switch will only send this packet to devices that have requested this address, this group address. And so by encoding part of the IP address we're looking for into the multicast address, we can let nodes filter on that address and only accept addresses that might be relevant to them. So this guy responds back, so it's from his address to my address, and he has given me the target link layer address to work with. So I now know his MAC address, and I can now deal with it up here. And then from this point on, I can just use his MAC address because I've cached it and I'll remember it for the future. So another protocol that ICMP v6 displaces is DHCP. So in DHCP, clients would send out a broadcast out to everyone saying, hey, I need to figure out where the network is. And the DHCP server would respond back saying, hey, here is our subnet mask, here is our gateway, here's our DNS server, all the good stuff you need. And so in IPv6, that also is done by ICMP instead of by DHCP. And that is called router advertisement. So my computer joined the network and it started by sending out a router solicitation. So it went from my link local address to an address called all routers. So only routers receive this. And it says router solicitation, and it just includes the link layer source address, so they don't have to do neighbor discovery to find me. So the router advertisement comes from the router's link local address and goes to, in this case, everyone. So router advertisements are some of the very rare protocols that effectively do a broadcast, so everyone can get this information. So if someone requests one, they can be like, it's only been 3 minutes, I guess I'll send out my 5-minute message early. And if it's only been a couple seconds, they might send it just directly to the node that asked for it. So this advertisement has a lot of information. So it's a router advertisement, so type 134, and we have information about the router itself. So in this case, it's a medium preference router, and nothing else is set. Oh yeah, now we can have more than one router in IPv6, which was kind of a weird thing to do in IPv4. But in IPv6, we have a bunch of them, and we can give them a priority of low, medium, or high. So we said our route lifetime is 1800 seconds. So we have to send a new advertisement within this time window or it'll give up. We also have a bunch of options here. So we have the MTU on link, which in my case is 2048 bytes. We have the link layer address of the router, which is just to avoid having to send it again. We have a type called RDNSS, so recursive DNS server, type 25. In this case, I've given 2 DNS servers here, so 53 and 54. And we have one prefix information. So this is what nodes will use to configure themselves. So it says our subnet is 2001 db81/64. The prefix is on link, it's autonomous, and so that means that devices are allowed to message each other on link, and they're allowed to add their own address autonomously. So autonomous is what we call SLAC, or stateless auto configuration. So basically the router will send out this advertisement that includes the subnet information, and it's up to clients themselves to choose their host address, or the suffix of the address. Since we have 64 bits to work with, it's extremely unlikely they'll choose another address that's in use, but they'll still do the whole neighbor solicitation dance called duplicate address discovery to figure out if that's true. This fact also means that a router advertisement is valid for everyone on the network. So unlike DHCP, where we'd send a specific DHCP offer of only a single address to a single client, a router advertisement in v6 is valid for everyone. They make up their own suffix, and everyone has the same information. One last step when joining the network is to do this duplicate address discovery. So basically, my address is 2001 db810 cof1 blah 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 blah, and I want to use that address, but I want to make sure nobody else is already using this address. So in this case, we're using that same link layer discovery technique of asking, does this IP address exist, to discover if the IP address that we are about to use is already on the network. So by sending a packet to essentially ourselves, we're proving that nobody else already has that address because they would have responded if they had it. IPv4 doesn't have any mechanism like this, so if you set 2 hosts to the same IP address in IPv4, things will just cause a bunch of hell. But in IPv6, we do DAD, duplicate address discovery. So coming back to my map here, last time we wanted to send a packet from my computer to the cable company to the hosting provider. We went from Chicago to Dallas-Fort Worth to Phoenix to the hosting provider. But why didn't we go up to Seattle instead? It's the same number of hops. Did I just miss something? So in routing at the IP layer, we have quite a lot of flexibility in configuring where routes go and how to prioritize some routes over the others. The general term for this is the route cost, but some other vendors use different terms like the weight or the distance. So those are things you'll hear. They all mean the same thing though, essentially. Essentially what this is, it's an arbitrary number where we would like to find the lowest cost route to a specific destination. And there are a lot of different formulas for calculating how the cost works. Different routing protocols treat them differently. If we're doing static routing, we can manually assign them. But for the purposes of this video, I'm going to assume that each hop has a cost of 1. So the more hops we are away, the more cost a route has. So I'm going to fill in this table, this routing table of all the different possible routes to this 2AO16969 from each of my routers. So here at Phoenix, it has cost 1. So over at LAX, it would have a cost 2 via Phoenix. And at DFW, it would also have a cost of 2, also via Phoenix. And at Seattle again, you have cost 2 via Phoenix. So now, if we spread out further, where can we push this route again? So we can send this route overseas to like Australia, We can send that guy to like Japan. We're going to ignore those. Atlanta is pretty obvious. So Atlanta, we're going to go via DFW, and that's going to be cost 3. But now at Chicago, we get an interesting thing. So at Chicago, there's 2 ways we could get there, both at cost 3. So we could take our cost 2 route to DFW and take one more hop to ORD, or we could do the same with Seattle. So in here at IAD, that's going to be a cost 4 route. And then YYZ, we have some options. So we could have a 5 cost route via IAD, or we could have a 4 cost route via ORD. So in this case, the fastest way is to go via ORD. And that's a cost 4 route as well. So back in layer 2, when we had multiple possible paths, we would use spanning tree to disable all of them except one to take us down to one possible path, and that way there was never any confusion. However, we'd really like to not disable huge numbers of links on the internet, so at layer 3 we have a much better solution. That's equal cost multipath. And just like we did in LACP on layer 2, we use the hash of some elements of the packet to decide what paths to take. So here I have an example packet full of fields. So version, traffic class, full label, length, next header, hop limit, source and destination, and then in UDP I have a UDP header. So source port, dest port, length, and checksum. So essentially what we'd like is we like some function that pulls out some of this data and possibly some of this data in the layer 3 header and the layer 4 header and makes a decision on which path we should take. In this case we have 2 paths, so our choices are 0 or 1. If we had multiple paths, we could say 1, 2, 3, 4, etc. However many paths we have, we wanted to compute one of that many. So we don't really care what algorithm we use as long as it always matches packets from the same flow together, so they always take the same path. Because it's possible that my example path through Seattle would take longer than my path through Dallas, and I don't want half of my packets taking longer than the other half. I don't usually care which path it takes, or I might use different weighting to take latency into account if it's such a drastic difference. But for example, if we had 2 different paths to Dallas that went through some Midwestern cities, the latency would probably be the same. We just want it to be consistent for all of our packets. So of the fields in this header, some of them will never change, such as the version, and some of them depend on the contents, such as the checksum, the length, and the hop limit. So the ones we can reliably match with specific flow are the source address, the destination address, the source port, the destination port, the flow label, and the next header. So that's 6 possible fields. So you may have heard of this called the 3-tuple or the 5-tuple, and these are essentially 3 or 5 different parameters we hash together to get a specific value to identify that flow. So 5-tuple function is a combination of the IP layer source and destination, so source IP address, destination IP address, and then the IP protocol or next header, so this would be the last next header. So if the next header is 17, that would be UDP. If we have a header in between, like a fragmentation header, we use the last one. So the inside protocol's header. And then the layer 4 protocol, which would be either TCP or UDP, we would use port, source port, and dest port. And so we basically take all of the bytes that make up these numbers, concatenate them all together, and take a hash function, and then take the remainder divided by the number of options we have. So if your clients are behind NAT, for example, they might all have the same source IP address. And so if we only used the layer 3 header, the IP header, we wouldn't be able to tell the difference because we wouldn't be looking at the port numbers. So the 5-tuple looks at those port numbers and tells the difference. Now the downside of the 5-tuple is, first of all, our router has to look into the next header. And we don't really want routers to look too far into the packet because it makes it more complicated from the process of the packet. So the 5-tuple method is really popular with things such as layer 3 load balancers. So if you're doing like a direct server return load balancer, you want to really consider all the fields in the packet. You might look at the 5-tuple, take a hash, decide what server to send it to, and be good. But for general routing on the internet, it's also common to use the 3-tuple. So in the 3-tuple, we have a different set of options. IP source, so where our packet came from, our destination, where it's going, and then the flow label. So what is the flow label? So IPv4 doesn't have a flow label, but IPv6 does. And a flow label is essentially a random number that is always the same for a specific flow. So if you have a TCP session, all of the packets belonging to that TCP session should have the same flow label. It does not matter what it is. It's assigned by the end host. It could be 0 if you want it to be. Usually it is either a random number or it's the hash of some layer 4 payloads. But the idea with this is that by putting this flow label into the layer 3 header, we can let layer 3 routers use that as a substitute for looking into the layer 4 packet, looking at the destination port, source port, things like that, and they can just look at the flow label. It's a number that should represent the same amount of data, roughly, same amount of variability. So by hashing the 2 IP addresses in the flow label, they should get pretty consistent separation and matching of packets. Now this also goes through NAT, so if your TCP session goes through network address translation, the flow label will be carried with it, so it's still a valid indicator even if your source and IPs aren't changing. So coming back to this diagram, I did another thing that you might have noticed. So this hosting provider here is advertising the same route as before, 2A01.69.69/32. We're also having another route, 2A01::, so it's all zeros, /64. So this is a more specific route, but it also doesn't overlap with the other one because it has some zeros. And then over here, the provider is advertising a different route, so 2A01:420. But they're also advertising this 2A01:00. And this server here has a 2A01:53 as the IP address, and so does this one. So what happens if we inject these routes into the routing table? What does the routing table look like? Ooh, wow, look at that. So we have 4 different routes from ORD to a router advertising this prefix. So we can go Seattle to Phoenix to hosting provider. We can go Dallas, Phoenix, hosting provider. We can also go Atlanta, Washington, hosting provider, or Toronto, Washington, hosting provider. And depending on which of these routes we take, we end up at a different server. So this is another magical feature of dynamic routing called Anycast. So essentially what we've done is we've added the same route from 2 different points in the network. So as the route spreads out, figures out its cost. Again, I have another video I'm working on for dynamic routing protocols because it's complicated. But anyway, these routes end up at our router here, and some of them point to a different destination. And we don't really know which one's pointing to which destination. We just know that they should all be pointing to the same resource, the same server. And so this can be used to geographically distribute users. So if you have a resource that you locate in multiple parts of the world, and the user accesses it by IP address, they'll get pointed to whatever server is the closest to them geographically, because that will have a less cost route than traveling around the world. So this is how really, really big companies distribute their content, especially DNS, but also content delivery networks will often use Anycast ranges like this. They'll advertise the same ranges from multiple data centers and let the routing system figure it out. So what this means is disturbances in equal cost multipath can cause us to end up at the wrong server. So if you're a network engineer working with Anycast, you definitely want to make sure you don't have too many Anycast points, because if a route flaps back and forth between 2 servers, the client will get disconnected. Nothing about the IP layer is guaranteeing that we always go to the same server. It's just choosing it based on the hash. So if something changes that hash function, such as the number of routes, if we had 4 routes, now we go down to 3, everyone's packets are going to get messed up because they're going to take a new hash now, suddenly. And normally that would just be a little bump in traffic as they reroute and find the new routes. But if you end up at a different server, that's a really bad day. So often, Anycast routes will be advertised from data centers. And within the data center, you won't use an Anycast, you use something like a layer 3 load balancer to forward to a specific server, not just the nearest server. So if you watched my previous video, Bridging the Ether, you might remember that back then we had 2 different types of traffic. We had unicast, traffic from one node to another node. We had multicast, which was traffic from one node to many other nodes. And in IP, we have multicast as well. So here's like an Ethernet broadcast domain. So we have some computers, we have the Ethernet segment. This might be a switch, whatever it is, Ethernet pretends it is. So Zoe here sends off multicast. It flows down the wire to everyone in the broadcast domain, and they can choose if they would like to accept it or not. So each network card can filter on multicast MAC addresses and decide if it wants the packet. So the packet could end up here, and it could also end up here. Now, of course, at the IP layer, we don't deal with MAC addresses, we deal with IP addresses. So how do we convert from a multicast IP address to a multicast MAC address? So here is a multicast IP packet. So it came from an FE80 address, that's a link local unicast address, and the destination is FF02:FB. So FF means it's multicast, 0 is some flag bits, 2 indicates it is link local, and FB is reserved for MDNS. So in both IPv4 and IPv6, we code some information into the multicast address to define its scope and things like that. So in IPv6, they always start with FF. The next digit indicates whether it's locally or globally assigned, and some other less common information. But usually that will be a 0, 1, or 3. And then the next digit indicates the scope of the address. So 1 is local to a host, 2 is local to a link, so it's a single broadcast domain. 5 is a single site, 8 is an organization, and E is global across the internet. So you might see a lot of multicast addresses that start with FF02. That is really, really common for things like MDNS and ICMP. So anyway, our address here starts with FF02, then it has a bunch of zeros, and then it ends with FB. So we come up here to the Ethernet frame, we start with 3333, which, because this is an odd number that is multicast, and then we end with 0000FB. So we just took the end of our destination address and stuck it in the MAC address. Now, one other thing about multicast, we can only multicast to a destination. We can't multicast from a source. That doesn't work. Our source address still has to be one of our unicast addresses, whether that's a link local address, a global address, ULA, whatever it is, it has to be a unicast address, and the destination can then be a multicast. So since we're replicating packets out to everyone on the network, so this MDNS query here would have gone out to everyone who has subscribed to the MDNS multicast group address, we can't use TCP. So TCP establishes a bidirectional connection between two endpoints, and we don't have two endpoints, we have potentially a lot of endpoints. So we're essentially limited to using either raw IP, so some protocols like OSPF do this, or using UDP, and UDP is extremely common in multicast. So another use of multicast here is a neighbor solicitation. So in this case, someone is looking for this address. They're probably doing duplicate address discovery because they actually don't have an address. And so they're sending a multicast to FF02:1:FFF11B49. So what is this address here? Well, it's FF, so we know it's a IPv6 multicast. It's a 0, so it's a globally assigned, and it's a 2, so it's a scope of link local. Where does the rest come from? So as I mentioned back in the ICMP chapter, this is called a solicited node multicast address. So essentially, if any node has a unicast address, it has to also subscribe to a group which contains the last 24 bits of its unicast address as a multicast. So this guy's unicast address ends with F11B49. So he took that and he put it at the end of the multicast group, F11B49. Then he prepended it with 1FF to get his multicast address. So this is the solicited node multicast. So the advantage of solicited node multicast over just doing a broadcast to everyone is that in theory only nodes that match this suffix will receive this packet, because layer 2 and layer 3 should be filtering these multicasts and only sending them to the right place. At least they could be on a well-designed network. So by using multicast for this purpose, we greatly limit how far these chatty broadcast messages go. And on something like Wi-Fi, the ability to restrict this can be really important. So other popular multicast addresses include FF02:1. This is all nodes. It's effectively a broadcast, and we really only use that for router advertisements. We also have a well-known address called FF02:2, which stands for all routers. So we send a router solicitation, and all routers should listen on this address to get the solicitation. Another one we have is FF02:16. This is for multicast listener reports. Remember how I said a well-functioning network can choose to filter multicasts it sends to host? Well, that works using these multicast listener reports from a protocol called MLD, Multicast Listener Discovery. It's part of ICMP, of course. Back in the legacy IPv4 days, this protocol was not part of ICMP. It was a different protocol called IGMP, Internet Group Management Protocol. Group, of course, meaning multicast groups. So anyway, anytime a node wants to receive data from a certain multicast, First, it has to configure its network card to allow that multicast. This is the Ethernet link layer. Then it needs to send out a multicast listener report, like this one, which asks the network, please send me this multicast group. So in this case, it's requesting a link local multicast group, so an FFO2, and so it sends its report to FFO2 as well, : 16. So all nodes on the network that potentially care about multicast groups can subscribe to this : 16 to receive these multicast listener reports. And usually these are smart switches and Wi-Fi access points. So in this case, they've got one message here, FFO2: 1, FFB3, C151. So this is another one of those node solicited multicasts. So this would float around the network to everyone who subscribed to : 16. They would receive this message, because it's a multicast of its own, and they would see that they need to exclude this from their multicast table. So essentially, by continuously sending these reports that say if they want to include or exclude a group, a listener somewhere on the network can build a picture of all of the multicast groups that are coming in a specific direction. So for example, if a network switch records what port each of these requests came in on, it can know that it doesn't need to send multicast frames at that specific port to a specific destination. And it can add to its multicast forwarding table in hardware which ports need to receive which MAC address groups corresponding to the IP groups from the MLD packet. Now this feature is often called ICMP snooping or MLD snooping, so it's the V4 and the V6 version. Very often ICMP snooping also does MLD snooping if the devices support IPv6 properly. Now this is really important to get right, especially for Wi-Fi, because in Wi-Fi there is no multicast effectively. There's broadcast, which gets sent to every Wi-Fi client at the basic rate, which is like 1.2 megabits per second. Or there's unicast, and so very often Wi-Fi access points will take a multicast packet that's only going to one or two nodes and unicast that to both of the nodes separately, because it's faster to do that at 150 megabits each than it is to do it at the basic rate of 1.5 megabits or 6 megabits. It's also why you got to disable your 802.11b and g, because those are bringing down your basic rate. Now, of course, this is layer 3, so we can route too, including multicast. So here's an example network that might be like an ISP. So they have fabric routers. They have different routers that service different customer groups. So maybe there's tens of thousands of customers off of each of these routers. They have some peering points, some peering routers into the fabric. And they have a data center, and they want to send TV from their data center out to all of their subscribers. So they want to get these packets distributed out to thousands of these hosts across their network, across their fabric. And how are they going to do that using multicast? So TV distribution is kind of like the best example of multicast. It's also commonly used for network time and precision time protocol. These are both other uses. But essentially, we're bringing multicast up into layer 3. So if we have a layer 3 hierarchy, we can copy these packets and send them out multiple interfaces as a way to multicast them, get them to their links, and then once they end up on the link layer, they'll get multicast from there to the individual hosts. So down here at the link layer, customers are going to be sending MLDs up to their router that says, hey yo, I want this specific multicast group that corresponds to a specific TV channel. So this router takes it in and switches from MLD, which is more of a link layer protocol, to PIM. And so PIM is a protocol that can get routed around all of these routers in the network and help them find the path from the originator. So here's the originator. We got to get this packet all the way down to the end. So each of these routers is going to end up with a forwarding table of which of their links would like to have the multicast. So remember, we have 128 bits of address, and we're only reserving 8 of those for those headers. So we could potentially encode quite a lot of information in this multicast group. Usually you would encode things like possibly the channel number and the resolution and things like that. So if you have multiple streams into the multicast group address, you would use the lowest bits, of course, because that gets encoded in the MAC address as well. So then from there, these routers are building PIM tables for each multicast group separately of how they're going to forward it. Then they have to figure out how to not duplicate packets. Because remember in IP, we use the hop limit. But for multicast, we're taking a packet and copying it in 2 or 3 or 4 copies. And how do we know that this other destination doesn't have another copy of the packet? So here's kind of what our routing table might look like. So I've artificially given orange the lowest cost here. So we have one cost via blue to the data center. And then all of the fabric routers have the same cost. So they're going to take their uplink if they can. And then down here, we're adding some artificial cost to some of the routes. So orange is preferred, then purple, then red, then green, specifically for this route. So we would probably have to do this using BGP. We probably can't do this with OSPF. So now we send our multicast down the network. So it ends up here the orange router. The orange router normally would look at its destination and look at its forwarding table and say, where is it going? But it's a multicast, so it doesn't do that. Instead what it does, it looks at the source address. And it does two things. So the first thing is it checks what its route would have been to the source address. So in this case, 2001 db869, that is via the DC router link, which is this link, cost 2. So we don't care about the cost here, we just care that this packet came in on the DC router link. Because if it came in any other link, then it did not come from the most optimal path to the source of this packet, and therefore it could be in a loop. So we should only be taking the least cost path. So if it came in from, say, here, maybe it would have gone down here and back up, and that's a bad thing, so we shouldn't forward it. The next thing is, now that we know which route it came in on, which is the reverse path, the path back to the source, we can flood this packet out on all 5 of the other links. So we can send it here, there, and these 3 down here. So now these 3 guys down here, they do the same thing. They look and they say, my best cost path is via orange, so I'm going to send that on my blue link and also my other 3 links to the fabric. So send it up to the fabric. So now this fabric router here, and I'll take the green one for example, it's going to look and say my best cost path to the source is via the DC router link, not via the many customers link. So I should drop the packet because otherwise I might create a loop. So essentially, by using the unicast routing table in reverse to look up the source address of a multicast packet, we can ensure we don't create a loop and that our packets get to every destination, flooded across the entire network. Now this does mean that if we use equal cost multipath with the same weight, we need to make sure the hashing function computes the same value on both sides. This is almost never true. So if we have 2 links and we're equal costing across both of them, then it's very likely that the hash that the other side would have computed is different from the hash on the sending side. So the reverse path might take, say, so this example, the reverse path might take the purple link instead of the orange link. If that were to happen, then our routers are going to drop these multicasts all over the place because they're coming in on the wrong link. So generally, you have to do some massaging of your routing table for multicast to work at this kind of scale. Now the other problem is we've now ensured that every single router here has a copy of this packet, and essentially every single network down here has a copy of this packet. That's a lot of copies of this packet. So one packet up in the data center going through a properly engineered multicast network could potentially end up at a whole bunch of customers down here. But if we have a whole bunch of TV channels for multicasting, maybe we don't want to send it out to all of these guys. Maybe we want to prune that back a bit. So that's where PIM comes in, Protocol Independent Multicast. So IGMP in IPv4 or MLD on IPv6 is what we use on the link layer to decide who wants to receive a multicast. So that's for layer 2 switches and first hop routers between the destination and the router. But once this MLD packet gets to the router, it converts it to a PIM packet, PIM. So PIM is used to build a routing table for multicast packets to disable links where no one at the end of that link wants the multicast. So in this example, if none of the customers down here requested this multicast group, this router would then tell its parent that it doesn't want the packet anymore. So up here at the fabric router, this one running PIM would disable this link, turn it white or something. So it's not going to send the multicast on this link anymore because everyone down here told me they didn't want it. Now this can actually work both ways. You can have PIM work in sparse mode, where it doesn't send any multicasts and you have to request them. Or you can work in the opposite mode, where it sends them by default and you have to request not to send them. Both of these are perfectly valid configs depending on what you're doing. Now, of course, this all assumes that the whole network is orchestrated to know that this multicast 400 came from source 69 and can do all of its routing with that assumption. But there's also the possibility that a node on any of these networks here could be sending the multicast, and we have to deal with it across the whole thing. So we specifically have different engineering at the PIM level for either multicasts that have a specific known source, and we can reliably build a tree up to that source, or ones that aren't. So I don't actually know of any application that doesn't use a single source multicast at this kind of scale. But in theory, IPv6 supports it. using a technique called a rendezvous point. So just as we did in layer 2, we have security measures we can implement on layer 3 to improve the security of our network. And right now you're probably thinking about stateful packet firewalls. And I'm going to get to those. But those are kind of a layer 3 and 4 solution because they look at port numbers. So I'm going to look at the simpler layer 3 only solutions first. So here's my example service provider again. So they might have 2 peering routers at 2 internet exchange points. They have some core fabric routers that go down to their end customer routers that go over, say, a PON circuit or Ethernet to their customers. And so they're getting progressively larger in bandwidth as these links go up. So one thing that could happen to this network is some specific IPs or specific customers could get a denial of service attack. So if a bunch of people around the internet start spamming junk packets at them, even if we're dropping them at the customer side, we're still overloading the network. So one way we can deal with that is a black hole route. So for example, we might be advertising a /32 out to the internet. So that's what's leaving our network. But within our network, we're advertising /40s. So this PON router might be a /40. Within that /40, we number out each PON circuit. Within each PON circuit, we take out a /56 per customer, so that sits here. So how can we block traffic just to this one customer without doing it all the way down here at their edge router or at the customer router? And we could take this specific route and send it up to the edge router. So our edge router here might have a route that says 2001 db8 420/40 via customer edge 5, which is this router. But then we add a more specific route for this specific customer that just says to drop it. So now if we get tens of gigabits coming in from our IXPs, all destined for this one customer, we can drop it up here at the edge router where we have a lot more bandwidth. So because this route was pushed out across our whole network, all of these routers here are all going to contribute to dropping packets to this destination. So if we get 10 gigabits each on each of these IXPs, this edge router has a 25 gig circuit. It's fine, it can handle that. Down here, if we were to be getting 20 gigabits, that might not be able to handle it at this level. So the same method can also be used to black hole specific routes for other purposes. So you can build a sort of distributed firewall for bad IP addresses. So within your network, you can distribute these black hole routes, and then traffic will never take bandwidth through the center of the network because it's dropped as soon as it exits a router that has that route. So you could use this, for example, for bogon prefixes that you don't want to leak, private networks as well. So for example, if you're running an internet service provider, you could drop the 10 prefix 172.16, those kind of prefixes, so they don't travel across your network and get lost. They just get dropped right away. So the next bit of security I have here resolves around routes. So here we have this host that's advertising this route. But what if I want to hijack some traffic to this? What if I set up an imposter over here? And what if this imposter starts advertising a more specific prefix? So over here we're advertising 2A016969, but here I'm advertising a 48 instead of a 32. So this would spread out across the network, and traffic intended for this server would get hijacked and go to this server. And with the same IP address, because it's hijacking my route, not my IP address. So how do we prevent that? So ultimately, this is something the internet was not really designed to deal with. BGP is slowly adding ways to protect ISPs from this kind of damage, but there have been many, many outages in the past caused by this exact thing happening. Often they're caused unintentionally by ISPs who are asked to block something on behalf of some authoritarian government, and they end up adding these black hole routes to their routing profile, and that ends up spreading out across the whole internet and blocking access to YouTube. But the new solution to this is called Route PKI. And essentially what that means is routes going through BGP can get cryptographically signed by their origin. So we validate that whoever originally sent out that route was authentic. Now this probably won't do anything for you on an internal network, but it does exist, and it's nice that it's being developed. So next drawing I have for you is mostly a misconfiguration thing, but it can also be a security thing as well. So we've got a customer here that's assigned a /56. So this guy here, he sends a packet out. So it's to 2620 FE, which is a DNS server. But in this case, he's spoofed the source address. So he doesn't have access to the source address. It's not the one assigned to him. He just made it up. Usually this is because he's trying to be part of a botnet or denial of service. So we would like to block that before it leaves our network. And we can do that using a technique called reverse path filtering. So this guy here might have a routing table that looks like this. So he's got his customer routes, which go down, and he's got his default routes, which go up to the internet. So he looks at this and says, what route would I have to take to get to my source address? and I would be taking the default route by the edge router. But this packet didn't come in from an interface that leads to the edge router. It comes in from a different interface. The interface leads to customers. So we're just going to yeet that packet right out of here. So this reverse path filtering is a really good way to implement at the edge of your network, like the customer side or the device side, to prevent them from spoofing source addresses of packets. Now, the packet wouldn't have come back to them anyway, so usually if you're spoofing the source address of a packet, which is not at all hard to do, by the way, in an operating system, it's because you're trying to do something malicious, probably a denial of service, or you've done some horrible misconfiguration. But either way, you should get that packet out of there as fast as possible. So the next technique we have is the stateless packet firewall. So we look at all of the fields in the packet, so what port it came in on, maybe the layer 2 MAC if we care about that, but usually what physical port or interface it came in on. We look at the IP header, so of note here again is going to be the source and destination address. And usually if you're doing stateless filtering, the primary thing you're concerned about is the source address. And you might also look at the layer 4 headers. This is a UDP header, but you could also look at the TCP header. So stateless firewalling is significantly simpler than stateful firewalling. So very often you use this to implement things like IP block lists. So you don't want any communication happening from these IPs. Usually this is where you do things like the bogon list. So bogons are IP addresses that should never be on the internet. They're not assigned or they're reserved for some other reason. So you don't want private addresses coming in on your public interface, for example. This might be a reputation or a geo-IP thing. So you might use a geo-IP database and filter out all of the IPs from Russia, for example. Add that to a stateless firewall so they get dropped early in the process. If you're running a mail server, for example, a lot of companies deal with IP reputation, and this is a really big deal in the email industry specifically, but some other industries use IP reputation as well in incoming connections. So with a stateless firewall like this, we can look into the fields of the packet specifically, the IP header fields, layer 4 header fields if they're there, and get that packet out of the system before we waste more time processing it at the stateful firewall. So next up we have the stateful firewall, probably the firewall you're most familiar with. So packet comes in from the internet, it is to us, but we don't know, it doesn't match anything in the state table. So then we have to look at the firewall rules and say, should we allow this packet to create a new state? And in this example that's a no, so we eat this packet out of here. So now, let's say our computer actually decides to access this server. So it sends a packet to the firewall. The firewall adds a line to the state table that says, so now we have an entry in the state table, packet goes out. So now we get a reply back. Now ordinarily this packet wouldn't pass our firewall rules because it's a random packet from the internet. But we look at the state table and we say we have a state that allows this source and destination, but they're flipped. So this is a packet that's returning from an existing connection, which was this one. So in that case, because it matches an established connection, we let it through anyway. Even though the firewall rules wouldn't ordinarily permit this packet on its own, we know it belongs to a connection that we already checked the firewall on. So fundamentally, that's the basics of a stateful packet firewall. And a big deal here is that we have to create a state entry for every single session that goes through the firewall. And this can be a big pain on memory and on routing, because it now means we have to have a memory entry for every session instead of just dealing with everything without state on the network. So we've broken the end-to-end principle somewhat by adding the stateful packet firewall. Another thing we've done now is we've made a funnel where all of our traffic has to go through this one box, the firewall, because that firewall has in memory all of the states in the state table. So if our packet were to come back through a different path, it would not go through the same state table if we had two firewalls, for example, and that would drop packets that shouldn't be dropped, which is a bad thing. Now for most people, you're not at the scale where you need more than one firewall at your edge, but if you do, that's a concern for sure. If you don't, using stateful packet firewalls is by far the bread and butter of modern security, so stateful packet firewalls are a good thing to help protect you. Now oftentimes they also do network address translation, which is a whole other topic that's not covered in this video. At this point, I think I've kind of run out of time to talk about the Internet Protocol. So hopefully, everything I've talked about so far gives you some good basis of information for how to debug and architect your networks. Now, I have a few more videos coming up in the series of how the Internet works. So I have a past video on bridging the Ether, layer 2 Ethernet. I have a couple other videos I've added to this playlist as well, talking about Wi-Fi and things like that. I've got at least 3, maybe 4 videos coming up already on my to-do list. So, I mean, obviously long videos like this take a long time to make, so I'm not going to have them out every single week. But up on my to-do list includes DNS, how the DNS system works, domain name system, resolving domain names, things like that. Network address translation. So this is what sort of broke the end-to-end principle that we used to love over the internet. And look how they massacred my boy. That's a whole episode of its own. And the third one is dynamic routing. So I didn't get to talk in this video about routing protocols specifically, but that's worthy of a whole episode or more on its own. How we do with things like RIP, which is the distributed Bellman-Ford algorithm, link state routing with Dijkstra's algorithm, OSPF and ISIS, and BGP. So those are going to come eventually. No promises, but stick around if you like the video. No sponsor for this video, so I really appreciate it if you want to give me a tip on Ko-fi. Link down below for that one. I have a Discord server, you can chat with me as well. We talk a lot about networking, IPv6, firewalls, Proxmox, virtualization, things like that. And I'll see you on the next adventure.